Hello, welcome to the Data Channel. So today, as part of the data engineering system design series, we are bringing the new episode about the CAP theorem for data engineering and why it is important, and from data engineering lens, how exactly we can kind of understand what exactly the CAP theorem, right? So let's imagine the scenario. So you are working as a data engineer for a global e-commerce platform, so that handles millions of transactions every hour, right? Suddenly, a regional database specific to particular region, so that database cluster will goes down. So customers cannot add items to their cart, but orders already placed are still being processed. So and in another region, right? So you jump in, checking your monitoring dashboard, you realize your system is still up, but the data across the region is inconsistent. So and that's where the CAP theorems like quietly step in. So the visible invisible law that actually defines how every distributed data systems behave under stress. So these are the stress situations. So how exactly the system is expected to behave. So that is what the CAP theorem like ask us the question as a data engineers, or from the implementers, right? So what exactly you can prioritize, or we can, like what exactly we expect from the system to behave like. So today we will deep dive into what CAP theorem really means for data engineers, how to balance in trade-offs, and how modern systems like Cassandra, like can take Cosmos DB, DynamoDB, Kafka are built around it. Okay. So before proceeding, if you are new to this channel, we would recommend you to please subscribe and also press bell button for instant notifications. So let's get started. So these are the topics that we'll be covering, like what exactly the CAP theorem is and why it really matters for the data engineers, and what exactly the CAP in CAP theorem stands for, and we will have some deep dive in all of these. And also we see the trade-off between these different CAP parameters that we're talking about, and which is quite important, and that is the only agenda of this particular video, right? So to understand how this can be traded off. And finally, we will see the case study for a global e-commerce analytics platform, and like we will have modern interpretation, and we can also see certain points beyond cap theorem, how exactly we can think. So with that, so we will move to the first part where we will understand what exactly the CAP theorem is all about. So let's start with basics, but we'll go beyond the textbook definitions, obviously. So the CAP theorem proposed by Eric, so in early 2000s, so states that it is in any distributed system, you can only guarantee two of the following three parameters, right? So according to that, so what he says is there are three parameters that we are discussing about. Okay, so that is about consistency, availability, and partition tolerance. So sounds simple, right? But actually, the beauty of this is like, and the pain lies in how these interact with how these interact when failure occurs, because these are not so isolated parameters. So these are actually like when the situation happens, when the issue happens, like these actually like complement each other, like are like if there is a issue of availability, then there will be issue of consistency. So like, or there is, if one consistency is coming up, availability goes down, so etc, right? So they actually work together. That means they impact each other, whether it is a positive impact or negative impact, so that is a different thing, but actually they work closely. So that is what we see, these might be different parameters, but they are still connected when it is coming to making the system like robust with respect to these three parameters, right? And consistency is nothing but means every user sees the same data no matter which node they talk to. Okay, so if I add a product in my cart, and you query my profile a second later, so you will see that updated cart, right? So and you can use a different devices, or you can access the same account from different location, so still you see the same the products that you have put in that card, right? So that is quite important. And the availability means the system always responds even if the answer isn't like most recent one, so that doesn't matter. But what it there's always a system is there, so to give certain response to you. And So partition tolerance, basically this means the system continues to function despite network failures or the delay that splits the cluster into isolated parts, because we are talking about distributed computing, right? So there will be splits from the like compute part, there will be split from the network part. So even then, like what it means is it continues to function despite it might be network issue or it might be delay in the split of the cluster into different isolated part. So that is where the partition tolerance comes into picture, or what we talk about, right? So here, according to this, in the real world, network partition will happen. So as a data engineers, we must choose between the consistency and availability when failure occurs. So that is what we will be discussing, why we will be doing that in the upcoming slides. So next we'll understand why CAP matters for data engineers, right? So now let's talk the realities. As a data engineers, we consistently design systems that collect, transform, and serve data across different distributed environments or systems. And it might be cloud warehouses, it might be stream processor, microservices, or storage clusters, etc. So when you build a pipeline that span across the data centers or cloud regions, so CAP is not theoretical. So it decides how your data behaves during accidents or incidents. For example, if you are designing a real-time fraud detection pipeline, so you would prioritize consistency because a single incorrect transaction flags could cost a millions of dollars. So, but if you are building a recommendation system, for example, a momentary inconsistency might be acceptable per se, and users see slightly outdated suggestions in exchange of high availability. So that might be still okay for the recommendation system, but not okay for real-time fraud detection pipelines, right? So every architectural decisions, so these are architectural decisions, replication factors, right? Quorum, like eventual consistency, retry logic. So trace back to the cap trade-off that you are choosing. So like you can have certain like fixes, right? You can have the data replicated into different systems so that availability is more and eventual consistency is more, and there is a retry logics you can implement. But end of the day, whatever, no matter what you do, so it will be around this which you want to compromise, like whether you want to like slightly compromise about consistency versus availability, and or availability versus against the consistency, right? So there is always a slight trade-off. So when we say you're compromising availability with consistency, doesn't mean that availability is completely gone. So we're talking about if it is 99.99%, that 0.01% or 0.1% sometimes, right? So for that, should you compromise the availability or consistency? We are talking about the bad scenario here. Let's keep that in mind. Okay. So that is where why actually the this CAP theorem matters for data engineers, and why you should be thinking to implement it in the system. So where exactly based on the different scenarios, based on the different use cases, you need to slightly think about this and when before implementing, so that you build that robust system. With that, we will see exactly what exactly the cap triangle. So we were seeing this image, right? So this cap triangle, and if you see here, there is consistency and availability where it intersect, and there is a availability and partitioning intersect, and consistency partitioning intersect. But there is no point where everything intersects and form the like ideal model system. That never happens in the reality. So that is what the cap triangle is trying to show us, right? And basically we will see what exactly each of these means, okay, in detail. But for example, like you take common database classification, right? Like if you take a CA system, that means you want to take availability and consistency. So then you can take MySQL, PostgreSQL, because work only when network is reliable, so, right? So that is where we choose. If it is a CA, like consistency and availability, you need to choose these databases. And if it is CP, that is consistency and partitioning is what important, and availability slightly you can compromise in the during the incidents. So then you can go for MongoDB, HBase, Zookeepers, right? So these databases. And similarly for AP, if you want to go, like consistency is not so critical in the incident, so then you can use Cassandra, DynamoDB, Couch Base, and Kafka. So it's basically again what you choose, right? So, and data engineering takeaway should be like choose based on your system's tolerance for downtime versus stale data. So what is exactly you can compromise, like some downtime of maybe 0.1% or like stale data for maybe 5 minutes or 10 minutes, right? So what exactly you want to do? So based on that, you can choose the appropriate system or the systems here. Okay. So with that, we will have some deep dive about what exactly the consistency means. So consistency ensures that once the data is written, all subsequent read returns the same value. In the systems like, as we discussed, PostgreSQL, MySQL, or HBase, transaction follows strict consistency models, but enforces it across distributed nodes, introduces coordination overhead. So think two-phase commit, right? So that is how it looks like, and both are designed to ensure that everyone agrees because committing data. So the cost, what is the cost? Latency and reduced availability when something goes wrong. So that is the cost you have to slightly pay for that. Okay. So that is all about the consistency. So next, if you see availability, availability ensures that every request you are having gets a response, even if it's not the latest one. It might not be the latest one. Systems like Cassandra, DynamoDB, and CouchDB choose this path. So they stay operational during node failures, but actually might serve slightly outdated data. So this approach is great for users facing system that can tolerate minor lags but cannot afford the downtime. So that's what we're talking about availability. Okay. So and there are different techniques to make sure the availability is there. You can replicate the data into multiple servers, multiple networking devices, have the load balancer in places, or like parallel systems which can take that like if there is any downtime, right? So the parallel systems can take over, and distributed caching you can enable. So that's the availability, right? So the critical system for that prioritize user experience and the uptime. So that is where the availability talks about. And again, there will be definitely trade-offs. So sacrifice, you need to sacrifice some data accuracy to maintain that responsiveness. With that, we will see the third one, which is partition tolerance, which stands for P. Partition is nothing but like partition tolerance is non-negotiable in modern cloud system. So when your services are spread across different regions or running on Kubernetes clusters, partitions are inevitable. So a node might crash, a region loses the connection, or latency spike beyond thresholds. So ignoring P is not an option, which means in practice you always sacrifice either consistency or availability. Okay, so but that doesn't mean that you sacrifice P also. P also might matter in certain scenarios. So ultimately, you can achieve the P, that is partition tolerance using again replication. You can have retry logics, asynchronous messaging you can implement. Okay, so by implementing these, you can make sure that there is some kind of partition tolerance inbuilt in the system. For example, Kafka continues to buffer even like events locally until the connectivity is restored. So in modern systems, network partitions are given, so P is actually non-negotiable. That's what we were discussing. And so now we will jump to understand the trade-off, right? So obviously, what we understood from CAP theorem is all three cannot coexist. So it is maximum at the any given point of time or any system you can build with two of these parameters that can actually go together. So again, it's the option that you choose when you're implementing or designing the system. When you talk about CA, that is consistency and availability, and again, you are choosing that system type. So you are compromising slightly on the partition third parameter here. So definitely there will be trade-off like of a strong consistency plus uptime. No partitions are tolerated, right? So that is the trade-off that you're having. And if you take real-time example, PostgreSQL, MySQL, these are the very real-time example where you can use this to make sure the CA part of the consistency and availability part is implemented, but slightly P is compromised. So it is good for small scale OLTP systems, transaction systems where you can still, because partitioning might not be required because the data is not huge or distributed. But in real time, if we really think, right, so this won't be the scenarios. Like OLTP systems will be usually huge, the transaction processing systems. So like ultimately you end up choosing the CP or AP in the real time, so that we will see how exactly that works. So definitely CA doesn't usually go together. So you have to think about choosing between CP and AP. So that is where the real game or real trade-off is. So if we talk about CP, that is consistency plus partition tolerance. So these systems prefer correctness over uptime. So if nodes disagree, so they stop serving data until the consistency is restored. For example, if you take HBase, Zookeeper, MongoDB in strict mode, so use these critical systems for if you have banking transaction inventory, financial ledgers. So because the data correctness is very important, and availability might be slightly compromised, okay, because the CRD operation that you perform, right, like CRD operation or CRD operation, like that has to be consistent. So there should be asset compliant, and the data should be really accurate, even though it is slightly taking some time. Okay, that is where CP, we need to choose CP systems. And if you talk about AP or CP, so then AP will be used where the systems stay available but may temporarily serve stale data. So data can be still compromised slightly. For example, you can use Cassandra, like MongoDB, DynamoDB, CouchDB. So these are great for real-time analytics and recommendation systems, or for example, social media feeds, where minor inconsistency is still acceptable. So there is no universal winner. So here it's basically we are talking about you can choose between different systems. You can choose between having the system which is CP compliant or AP compliant. Okay, but like definitely there will be trade-off, and you cannot. You need to choose what the business needs, or what is the business trade-off. What is the problem that you're solving using your particular application. So based on all the scenario, you need to choose this CP versus AP. So as I said, CP versus AP is the real game. CA doesn't people mostly doesn't think about that, because in real time you don't get that CA because like consistency and availability doesn't usually don't go together. So you need to choose either between CP and AP, right? And CA, making CA available, also there are a lot of systems which are not there, and the systems which are there also doesn't serve the huge data or data at scale. So that is where CP and AP, you need to choose it accordingly. So now we will move on and see how exactly CAP impacts data engineering design. So for example, you are beginning the start of the project, and you are part of the designing team, and you are responsible of the design of the entire data engineering system. So then you need to know about all of these points. So the first one is pipeline design and trade-off. So every distributed pipeline, distributed data pipeline faces CAP trade-off. So whether it is ingestion, transformation, or any performing any analytics, right? So we cannot optimize all three. So we need to choose based on the business priority. For example, if you are building a streaming system, that is AP, right? So in systems like Kafka, Spark streaming, so we favor availability and partition tolerance. So ensuring continuous data flow, even during minor failures, accepting brief inconsistencies. So if you take batch systems, so where we talk about consistency and like a partition tolerance, that is CP, this is in data warehousing or ETL processes, we emphasize consistency and partition tolerance. So where we need to pause the jobs rather than risking the incorrect analytics. And so like from architectural thinking also, right? If you think of a mature data engineering design, so hybrid architectures where some layers are CP and others are AP. So achieving both like correctness and uptime. So is mostly the edge cases we'll be handling that way. And finally, we have decision drivers. The right choice depends on the latency tolerance, data criticality, and business SLAs also. And CAP helps you design intentionally, not accidentally. So that is where, so the CAP needs to be discussed, needs to be well understood, and so that the business is also well aware how can this trade-off work. We need to take this with the business and understand what exactly works best for them and best for their system. And that is where you can choose between You will always have the trade-off between AP and CP and choose between them. So with that, we will quickly move on case study for global e-commerce analytics. So here we will see, we will take a scenario, right? So the scenario here is a global e-commerce platform replicates order data across regions. So that is where the scenario is. And so what we are choosing the network partition here is EU and US, basically the different region clusters are loosely connected. So if the system prioritizes the consistency, that is CP, then order pauses for EU users until the synchronization happens. If the system prioritizes AP, that is availability and partition over CP, so then order continues, but the users might see old stock and old stock count and delayed updates. So this is the scenario or constraint for that matter for this scenario. So here we can choose, right, when we talk about the cap. So we can, when a network partition isolates one region, so the ingestion layer must choose between the consistency and availability, obviously. So if you choose AP, so streaming pipelines keep running, collecting local data, ensuring uptime before accepting the temporary data drift. And if you take CP, choose CP as a priority system. In that case, critical systems like payment or inventory pause right happen until synchronization resumes, ensuring accuracy over availability. So there is the hybrid also you can think of, where real-time dashboards are using AP model and financial reconciliation is using CP model. So this layered structure strategy ensures business continuity without compromising the integrity. So the key thing here is to notice there is no perfect cap position. Okay, only context-driven decision or context-driven design decisions aligned with the business risk and data criticality is where you need to strike that balance and choose between. So with that, we will see the modern interpretation, how exactly this looks like, right? Evolving, we need to think about from the CAP. So modern cloud systems have blurred the CAP boundaries, offering configurable consistency and intelligent fault handling. For example, Google Spanner uses true time for global consistency. Cosmos DB provides five tunable consistency levels. Kafka basically achieves a near strong consistency with idempotent producers. So there are also advanced techniques systems uses, right? So basically quorum based reads, right, and the delta transaction logs to balance the performance and reliability. So architectural shift also that is happening, right? So that is, instead of choosing between two, engineers now design gracefully degradation, maintaining partial availability with controlled consistency. So key thing here is to understand CAP is not a limitation; it's a design lens. The mark of senior data engineer or a data architect is knowing which property of the property to prioritize and when to prioritize and why to prioritize. So that's quite important. So we are coming to the end of the video. So to summarize this, right? So no distributed system can achieve all CAP simultaneously that we discussed. That is a key takeaway. And partition tolerant is a must. So the choice is usually between the consistency and available. That means whether you have to choose CP or AP. That is where the decision lies. And so CP principles to business context, how it maps is like if you are having financial systems, choose CP. If you are having streaming data, choose AP. And for example, local ETL operations where you're performing, right? So then you can choose CA. Within the single environment, you are having some POC, whether you're doing some MVP related stuff. So you can choose CA. CAP helps data engineers justify architectural trade-off with data-driven designs. So that is where you can go and convince the stakeholders that why this is important and why the trade-off is important. So true mastery is when we know to relax one property to serve the other business goal. So that maturity has to come within the data engineers architects, and also it's like a business also has to understand this, and they should be made available or they should be made aware of this the trade-off, so that you can take them to the consideration and work along with them. Okay, so with that we reached the end of this video. So definitely hope this video was helpful. So if it is useful, please comment in the comment section and also share it with your colleagues, right? Hope this was useful. Thanks for watching.